Okay, we are recording. Welcome everyone to this. I'm not sure how many numbered stateless Ethereum call. We have Neville today, who's going to present the analysis that he and his team have worked on for the impact of gas pricing for code chunks under Verkle tries. Trent has just shared the link in the chat. Yeah, Neville, take it away. I guess it probably makes sense for you to just like walk through the report, kind of give a summary of your findings, and then we'll move more towards like a Q&A and open discussion.
Sure. Okay. So I prepared 10 short slides. I'll just go through them. It's going to take around 15 minutes and then we can discuss between ourselves. All right. So, okay, well, I guess everybody knows the context in which this study has been carried out. Verkle trees exploit the polynomial commitment schemes, and because of this, there's an opportunity to reduce the witness sizes. And so, you can come up with these stateless clients, and the block proposer can then just send the relevant state witnesses together with the rest of the block. Now, the crucial part is that the contract code is part of the state. And so any code which is executed or at least accessed, for instance, using code copy, that needs to be metered too, right? And the way that has been proposed is that the code is going to be chunked into 31 byte segments. Why 31, not 32? It's because you need 1 byte at the beginning in order to see how much push data there is, so that in order that you can parse that individual chunk. Okay, and so obviously changes to gas prices can break contracts, and in this case, they may also render some smart contracts uneconomical. So the summary that me and the rest of the team at DDOB conducted was over some of the recent blocks. So that's 12.9 to 12.95 million. So it's a pretty representative sample of currently executing contracts. In terms of net increase in gas costs, that's around 26%. But it's interesting to see on the right-hand side how that 26% is represented by. So the current proposal decreases the cold gas cost when you've got adjacent storage slots being accessed. You see, if you are accessing, for instance, slot number 0, typically that's owner, and then another slot after that, then you amortize the cost of the cold the cold access of those two. And so the state access costs are reduced, but then of course the code chunking, so for every 31 bytes, which needs to be loaded, you need to factor that in. That increases the cost significantly. I mean, as I said, we estimate around 26%. Okay. It is also interesting to see that the way that the study has been proposed, when you load certain information about the contract like balance, the first 64 locations of storage are also in the same subtree. And so you only need to pay fewer gas costs for getting some of the first few locations. And then the rest of the storage instructions are chunked 256 at a time, right? And so what that means is that if you've got, flat global variables, that's fine. They're probably going to fit in the first 64 locations. But when you use maps or when you use arrays, every one of these will be, and in the case of maps, every different key value will be in a different subtree. Okay, so adjacent storage locations, cost reduced from 1,900 to 200. Then you've got the chunking mechanism. Every 31 bytes of fresh loaded code, that's 200 gas. And then you also need to pay a much higher gas cost when going through different subtrees. And theoretically, you can have, in practice, you will have multiple subtrees for large smart contracts. Okay, and we'll see how that manifests itself in some pathological cases. Right, so in order to conduct this study, we did two experiments. We wrote a static analysis client on top of GigaHorse toolchain, which is an EVM binary code lifter, right? And we wrote a path-sensitive analysis, which can find the worst case gas cost increase only for code chunking. There's an API available. There's around 30,000 contracts which were used recently there. Yeah, we found a few fallback functions that will break, but there was nothing too serious exposed by that experiment. In fact, none of the experiments exposed anything which is serious. But it was more interesting than to carry out a dynamic analysis where we modified an Aragon node to store not only the current gas cost per internal transaction, but two different things. So you've got the storage called gas cost for the post-Berlin semantics, right? So we've got those access lists that have been proposed for the EIP 2929. We re-implemented those so we can track how much is the cold gas cost in that system. And you've got the current proposal, which is slightly more complex. We also implemented that. So we are tracking both the cold gas cost in both versions. And then separately, there's also the code chunking cost. And by adding these or subtracting from each other, we came up with some interesting insights. Okay, and all this data was combined with the contract library blockchain explorer database. Information is per internal transaction. And now we could actually look to see some extreme cases in some of the most recent transactions. Okay, so here's an extreme case. Now I'll go through this, right? So we've got, okay, let me find this contract. I think it's this one, right? No, it's this one here. Yeah. All right. So this is the decompiled view of a smart contract. This is Uniswap v2 router 2. Okay, and this is a very simple getter. Now I'm viewing the decompiled version of this. It's similar in the source. Just give me a second. Oops. Yeah, just give me a second. Yeah. All right, so this just returns a constant. And because it returns a constant, you would expect the gas cost to be pretty low. But because of some pathological behavior in the function selector logic, so the function selector logic, the decompiled version, which shows you the function selector logic, this is how it would look like, right? Because there's certain basic blocks that one would need to jump to, which are far away from the initial part of the contract. And we can see this in a trace over here. All right, so this would be, for instance, this would be the instruction number in bytecode. Okay, so the byte number. And all right, so the function selector ends here. And then you've got a large jump here. Okay, so it jumps to an instruction which is quite far away. And so you have to pay that extra price of the going from one subtree to another. And then the Solidity compiler adds that not payable check, which is compiled to another chunk which is further away, right? So you need to pay the price for that again, right? And we're talking, 1,900 units of gas each time. And then, there's other costs. And so for this particular, for instance, getter, which should currently be very cheap, it's actually quite expensive with the new Verkle gas costs. Another interesting example is the curve gauge function selector. Okay, so this is written using Viper. And let's look at the function selector code. Okay, so it's not the best decompiled representation, that is true. But what to keep in mind is that in this Viper contract, the function selector is implemented using a linear search. Okay, so if you've got a function, say for instance, which matches the following signature, then the execution needs to compare to all of these different ones. And then what tends to happen in Viper is that if the condition doesn't match, you jump away to an instruction which is further away. And so you waste the rest of the code chunk that you have loaded. So you get, an order of magnitude increase in gas cost because of this on some of these functions, especially the getters. Okay. On the other hand, there are some projects that are positively impacted. For instance, this is a smart contract from Synthetics, which returns a number of different fields within the same struct, okay? And since those are obviously going to be stored adjacent to each other, okay, so since they are stored adjacent to each other, the cold gas cost is amortized, and so it's much cheaper to execute this getter than it was in the post-Berlin semantics, okay? We also checked to see whether there's some particular compiler version which is causing these issues more than others, and really we couldn't come to a conclusion. Okay, so in summary, there's some recommendations that we have. Okay, so the Ethereum Foundation could consider lowering the chunking cost initially, right, for the first few months, so that developers can have time to improve their contract and compile.
Sorry, by chunking cost, you mean the cost of accessing a new chunk and not an adjacent chunk, right?
Yeah, a new chunk from, say, from 200 to 100. The branching factor in the Verkle tree, now I understand that there's some cryptographic chunk right now. And then there's also a case where sometimes you get smart contracts like in Aave, for instance, it has a fixed number of contracts where it calculates the the position for a particular user, and so it calls the same code for the different A tokens, but that code is deployed to different addresses, and so you have to pay the same chunking cost every time, even though it's exactly the same code. And so if the code is then indexed via the code hash, it will optimize that particular case. For developers, of course, if you group frequently accessed storage locations together, and so if you, for instance, instead of having two different maps, which are indexed by the same thing, you have one map, and then the value would be a struct. That's obviously going to be much cheaper to do it like that. Then the compiler developers, they might be able to develop higher level primitives, like for instance, safe add, and then pack these into the first 128 chunks of a smart contract and reuse them every time. Because you don't pay a price for jumping and then jumping back. It's like 10 units of gas and 10 units of gas to come back. But accessing a new chunk, that's 200 units of gas. So it's an order of magnitude more. And generally code within a hot path, so a path which is more likely to be executed in the contract code, should be packed closer together. There's an example in the next slide. So currently the function selector logic is right. So there are no loops. It's like this, right? So you've got conditions which are compiled into code like this, which means that for every one of these that you access, you are going to pay an associated chunking cost, maybe more, right? For each one of these conditions that you hit. Whereas if you put these into a loop, so for instance, right here, this is some pseudocode which I just wrote today before the meeting. So this particular loop will be executed log n of the number of selectors, right? And it's a little more expensive compared to what's currently being generated. For instance, it uses code copy and it uses a few more instructions, but the code chunking cost is much higher than executing EQ or jump I or GT. Then for instance, packing the function selectors, so the 4 bytes in a part of the bytecode means that you will probably access half of that part of the bytecode, and the rest you will not access, so you'll not pay a price for that. Yeah, and the black stuff, it only gets executed once, so it just adds a fixed cost. So there's some tricks that compiler developers will come up with, right, to optimize for this new semantics. And this red part, which is the code chunking cost, which is what's adding most of the gas cost, that will be reduced probably. So in conclusion, the impact is not negligible. You've got 26% gas cost increase on average. However, this assumes that it's the code will remain the same, that the compiler developers will not come up with better optimizations, and that the engineers, they will not change their code style. And in any case, the gas cost can be increased a little more gradually. Of course, this impact has to be gauged against other factors. All right, so that's what I had prepared. We can go through questions and maybe more things in the report.
How does this 26%? So I mean, there are two different costs, right? There's the cost for accessing a new chunk, but with this last byte the same, like the same suffix, which is cheap. And then there's a more expensive one where you access like a completely unaligned one. Have you quantified what the contribution of each of these is to the 26%?
So in the extreme cases, the ones that we saw, the contribution would be significant. I haven't quantified them separately, to be honest, but I would think that it's the I made a rough calculation, and it's the 200, which is the highest, which is the one which contributes the most towards that 26% that we saw. Mm-hmm. But in the extreme cases, it's the cost of executing the different subtrees.
Right. And basically, so in the examples that you've shown with like the selector, linear search in the selector, would most of these jumps that you have there, would they be within like the same sort of suffix tree, or would most of them access a completely new suffix?
So most of them, they would be within the same subtree.
Okay, so it would still be the cost of 200 and not 1,900.
Yeah, however, then you jump into a function, for instance, in one of the previous examples, the not payable modifier is actually reused across the different functions, and it's been compiled in a very further away part of the object code. And so that adds an extra 1,900, just that little modifier there, not payable. Yep. And of course, 1,900 is nothing if you're doing storage changes, right? So yeah, so that doesn't contribute much to the 26%. It's the 200 gas cost.
I mean, that's very interesting because we have a new idea for modifying them, or like a likely way to modify the Verkle try construction, where we can probably lower that 200 and maybe, I don't know, halve it. Or
well, I mean, keep the 200 number was like designed entirely around witness data size. Like it wasn't even taking into account like attempts to figure out how long computation would take. Yeah. I mean, I do think that realistically it's possible to reduce it slightly from 200 just because like it's like I think branches what's the worst case for a branch? I think it's going to be going down like about like what 14 or so times 32, like probably a bit under 500 bytes, and that's about 2,000 gas, so about 4 gas per byte. So like if we want to knock code chunk costs down to the 4 gas per, I guess maybe the 4 or 5 gas per byte level, that would be like
so that would be 128. Which is
128 as a minimum, and then 150 as like a safe number.
Yeah. Just to clarify, has it been like, is there a difference? Is there a main contributor between the code? Because it seems to me like you're focusing on the code accesses. So you mentioned the data access at the beginning, and then not really anymore. I was just wondering, is the data like the data access, insignificant compared to the code access, or is it just?
What do you mean by data access?
Like storage slots.
Oh, I see. Well, I guess, data access, storage slot access is being charged for already, right? Like post Berlin, every new storage slot charges 1,900. So actually, this particular gas cost change will make it cheaper to access storage, because if you access storage that's in the same size 256 sub-range as something that you accessed already, then the cost goes down from 2,100 to 200. So like, for example, if you look at Uniswap, the Uniswap v3, the contract has like a whole bunch of storage variables at the beginning that a lot of them get accessed. And those storage variables would end up mapping to slots like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And so like they would end up like basically replacing like 10,000 gas worth of reads with like basically just like 2,000 plus another like a few hundred, so less than 3,000 total. So like that's the place where the gas savings come from for at least those lucky contracts that you get gas savings from this change.
Right.
Yeah, and of course, the thing about maps is that each value will be stored obviously in a different subtree, but there might be some optimizations, but they're like, you'd have to restructure the storage schema of your contract.
Right.
So I don't know. I could share a few more examples if you wanted to.
Are there any ideas anyone's proposed for potential ways we could restructure maps so that they are more conducive to chunking?
I guess like one simple idea is that if you have a map of a struct, actually, I forget, does this happen in Solidity already? Like if you have a map where the value in the map is a struct, then do the structs still get stored contiguously? I
think so.
If not, okay. I mean, if not,
like I'm thinking more just like
should.
for tokens, like tokens being one of the major things on Ethereum right now. Is there a way we could go with tokens that doesn't suck?
Well, the challenge is that for tokens, the average access is going to still be pretty random, unless like you're talking about things like, the approvals. Well, no, approvals are also a two-dimensional array, so that's a bit different.
I'm thinking more like,
okay.
Because this is transaction wide, right? So if you could do a Uniswap swap, a token or any other app, oftentimes the same token will move like 3 or 4 times. And it would be nice if that, didn't incur, 3 or 4 code chunk hits, if possible.
Don't you, in those cases, get saved by the fact that relying the token, if a slot goes from 0 at the start of a transaction to 0 at the end of the transaction, because the token entered the slot that place and then left it again?
No, that saves writing costs. It does not save reading costs.
Yeah, it doesn't help with the code chunking part.
Yeah, okay. Okay, I mean, one very specific thing that you could do, I guess, is you could like store authorizations or approvals as being like just an array instead of storing them as a map, and then you just store them as a struct, so they're kind of right beside the you would store them as a struct right beside the balance, and then like some of the time you'd be able to save a bit of gas. I mean, that does add a bit of some complexity, but
in general, it sounds like we don't have any great ideas for getting mappings of things to consolidate at all, right?
Yeah, no.
Like at the moment, we have no great ideas. Okay. That's unfortunate, but understandable.
Yeah, I guess. Let's see. I think, like, realistically, the savings for that sort of stuff are probably going to come from like whenever we have any flavor of account abstraction, so that approvals can just be part of the same transaction, and that'll probably make up like anything that this whole thing loses, at least in aggregate.
And so the storage location optimizations, that's going to be hard to do by the compiler because of aliasing. It's something that you would let the developer do.
Yeah.
By the way, I'm just like staring at the inside of some Uniswap transactions, and like even in there are like, it seems, maps of structs inside Uniswap, and they do get stored adjacently, and like accesses that are adjacent happen. And so, I mean, admittedly, I'm looking at writes rather than reads here because I'm just looking at a trace of what's been written. But you've got quite a few places where like a slot and then a slot that's like 2 later has also been written. So I suspect there's actually quite a few savings in like more complicated contracts, but it's just like the simpler stuff where you don't get these benefits.
Okay.
That's Uniswap v3, I'm assuming?
Yes, specifically v3.
So this might be a dumb idea, but what about implementing the maps as a try instead? Since contiguous access would be faster, it could get you saving in some cases.
Oh, I see. Like I actually am making a tree inside a tree.
I mean, that's already what it is with the current model, right? Because the storage tree expands into its own, the storage tree expands out of the account tree. So it would be going back to the same model, really.
Yeah, but each map would be its own tree. Yeah. kind of hard to visualize just like this.
Yeah, I mean, like I guess you could like make any map better by just having a like size 128 like least recently used cache or whatever. Like basically, yeah, like split all keys into 128 buckets, and then for every bucket, like you would just also store the most recently seen value in some particular place. And then if you need to like read or write the most that you would just update it there first. It's
Oh, yeah, that worked pretty well, I think. And you also do more.
Let's not forget, that currently, like safe add and things like that, all of those implementations could be reused, right? They could be compiled. Someone could come up with a higher level DSL, and that each super instruction would fit in 31 bytes, and then you would only jump to that and back. Right? So that reduces the size of the code significantly. And so there's less code to load.
Yeah.
I'm not a regular on the call, so I apologize if this has already been asked in the previous call. Have we gone over the kind of worst case scenario on mainnet, like for the past year, in terms of how much any given transaction would increase as a percentage in gas cost?
So that's been conducted per internal transaction, because it's more interesting to do that, so you can identify a specific project. But
sure,
around 15x higher gas costs, but that doesn't mean much, because we're talking about a getter of a constant value, for instance, or a getter of a single storage slot.
Like one example of a legit function that would be seriously harmed is if you make it, like some cryptography libraries that depend on pre-computed 32-byte values. So like, for example, take a Pedersen evaluator, where I think it was that might have been actually one of the examples, right? Like basically, like for the Pedersen evaluator to be efficient, it just stores pre-computed a bunch of multiples of an elliptic curve point, and then it just, based on the thing that you're multiplying the points by, it just picks a random subset, or it picks the appropriate subset of them and then adds them. And the basically what that does is that lets you do less elliptic curve additions in the EVM, because you're using the pre-computed one, the pre-computed points, but it requires all these random accesses. But the challenge, of course, is that a push 32 goes up from being 3 gas to being, in the worst case, in the worst case, 400 gas if you if you end up really unlucky with the boundaries. But like the more realistic worst case, 200 bytes. So that, like, I think in that situation, like if once you start optimizing for witness size, like the optimal trade-off just kind of goes back down toward a smaller sized libraries, and there's not that much that can be done about it.
Do we have an idea if anything on mainnet today would be broken in the sense that it can no longer execute at all, like within the block gas limit?
That seems intuitively unlikely, especially because London doubled the block, the maximum limit, and then on top of that, there is of course the recent gas limit increase, and things that cost 10, like, well, most people don't build transactions that cost 10 million gas, because there's just a bunch of safety reasons not to do that. But they like the things that do tends to be more contract creations, and don't tends to be like big cryptography things, because they like basically anything that needs to be done more than once, if it's big enough to be to fill up a block, then it's too expensive to expect users to do more than very occasionally.
Right, and we don't believe those types of actions are the ones that we'll see the 10x or 15x increase on, right?
Well, contract creations are definitely not going to see the 10 to 15x. I guess what else is there? There's like, I guess the current version of the optimism fraud prover, but that's also like I don't think it uses any pre-computation tables stored in code. And as a rollout strategy, I do like the idea of like just whenever the hard fork happens, just having a built-in kind of increase over time schedule for the code chunk cost.
Doesn't that make us susceptible to DOS attacks during that time? Like the whole idea is the gas cost should reflect DOS cost.
Right. Well, during that time, it basically means that like running a stateless node safely will have higher system requirements. So yes, so yes, during that time, like running like that will weaken stateless nodes, but yeah, but it does. I guess the like one counter argument would just be that like, well, during that time, people are going to be twiddling around and figuring out stateless nodes in the first place, and so it's not going to be that mature anyway.
Yeah. So if I understand correctly, you're basically saying like people running full nodes can run without introducing DOS vector at the lower lower gas costs, and it would only be the stateless people that are perhaps at risk, and we won't have any of them at launch, and so we don't have to worry about that at launch.
Yeah, pretty much.
That makes sense.
I mean, I guess in that case, the question is, we don't even like we might even have like two separate stages of this. Like the first stage is introduce Verkle trees, and then at some point later we enable, like, because that also needs all kinds of networking work, like we enable stateless nodes, and in between
well, enabling stateless nodes would not require any consensus changes beyond past that point, right?
Exactly. Yes.
Right. I mean, realistically, I expect a high chance that like Nethermind's people are going to get excited and just like build an awesome prototype, and like somebody will use it.
That would be very cool. Yeah.
Yeah, that somebody can buy a big machine.
Oh, another thing is that if it's specifically code chunking costs that start off being at say 50 and then ramp up to 150, then the stateless node implementations could start off as being partially stateless nodes that still sync all the code, or at least that store the code, that any code that they see. So they're like they do the equivalent of like beam sync for code and then stateless for everything else.
Another thing to consider is like in the initial phase, there's also not much like incentive to DOS the light client, the stateless nodes. I mean,
yep, that's true.
Why would anyone do that? So I guess if the average, as long as the average costs are okay, maybe it is okay to only get DOS protection a year later or so.
Is there a risk that like just no one is that we're going to introduce it at the lower rate and it will be like fine, it's not going to affect anything, so no one will do anything for like 6 months, and then we put it up and everything breaks and people start getting around to actually fixing things?
Like basically, like will people just not bother fixing until the gas cost goes all the way up to like 150 or whatever the final level is?
That was the question, yeah.
Right. I guess that's always a risk. But I guess the idea is that like the step up function is already the like close to the best mitigation that we can do, because like it would already get users complaining about gas cost increases. So Yeah.
You could do it probabilistically. One in 100 transaction has to pay it in the beginning, and then you ramp it up.
So fun.
Or 1 in 100 blocks.
Yeah. Right.
I think we also have the benefit of people like the Solidity team. We have open lines of communication with, and they can participate pretty heavily in helping with getting people moving forward and getting more Verkle tree optimized contracts. So I think that'll play a big role. Like if Solidity starts getting updates out. That being said, people do run very old versions of Solidity to compile their stuff. So this is not like a full solution, but it does help just get people upgrading without even realizing. Like they don't even know they're writing better code. They just are because the compiler is improving.
Yeah, in fact, during the period of the study, most of the contracts were not actually Solidity 0.8. So the question is, could minor versions of the Solidity compiler optimize, the function selector code, for instance? Or is this like a major change?
I think it would be, from a Semver standpoint, I think it can be a minor change, assuming a minor or a patch, because there's no API changes. That being said, I don't think Solidity has a history. The Solidity team has a history of doing patch versions to old versions. So it would probably be like, 8.0.2 or whatever's next. I feel like it's unlikely they're going to release like 4.12.7 or something.
Right, because during the period of the study, there were almost as many contracts that have been compiled with 0.6 deployed as 0.8.
And that doesn't surprise me, sadly.
I mean, it's an ongoing discussion to have long-term support versions of Solidity, but unfortunately it's not happening yet. I don't think they even backport bug fixes.
So on that topic, I suppose one of the bigger conflicts is that some auditors recommend the old versions. And especially the problem comes out when somebody is building on an existing project, which usually happens if they, in DeFi, if they build on like other EMMs or anything like that. And yeah, I guess then the other big one is building on Aragon, because those, the way you want to extend that code base, you have to keep using the same version of the contract. And I think Aragon itself is like 0.6, no, it's 0.4 something actually. And the other like EMMs are 0.6, 0.7. So even if you want to build on 0.8, in many cases you cannot.
Yeah, that's a good point.
I wrote some code that like interacts with Uniswap v3, and I was just like, I have to use all these Uniswap v3 libraries. So I looked at what Uniswap v3 compiled with, and I picked that compiler because I didn't want to have to work out whether the new compiler was going to break the libraries I was relying on.
So the new compiler in most cases wouldn't actually break, and it would work with the old one, with like the older sources, but each of the source files start with a version setting. And that version setting is flexible. It could just specify the minimum supported version. But actually the recommendation by auditors is to use a fixed version number, not even a range. And in that case, if the library you import has like a fixed version, there's just no way to do anything, but either you change that line in the imported file, or you just keep using the same version in your code.
The thing that was concerning me in my particular case was that you had code that probably relied on overflows overflowing rather than erroring, and that got changed to 0.8, and it was just, I just don't want to deal with this.
Yeah, that's actually what the Uniswap team said when I suggested they upgrade to 0.8 before release. They're like, we'd have to rewrite a bunch of stuff.
So,
Okay, so no free wins from Solidity updates, unfortunately, it sounds like. Nonetheless, I mean, for me personally, not that it matters. The current plan seems reasonable to me. Start with low cost, ramp them up over time slowly. As much fun as probabilistic ramp up would be, I think it makes a little more sense to just iteratively do it. And that can be over, a year or something.
Yeah, we can check how much it would cost with 100 and give you an answer. So that 26%, for instance, goes down to 15, for instance.
I'm not terribly worried about the percentage gas cost. Like at this point, I hope that everybody understands gas cost change, and you need to be prepared for that, and you need to code against it, and you need to design your economic systems against that. And if it's not an order of magnitude on average, I don't worry too much. I worry a little bit about like the worst case scenario. So if you've got some contract that can no longer execute, or some contract, it's reasonable to expect your contract costs 15 or 20% more. It's perhaps unreasonable to expect your contract to suddenly cost 7 times as much. Like that's not cool. If most contracts are kind of close to that average, I don't know if we have like any other distributions besides average, but if most contracts fall kind of close to that, for me, that seems reasonable and acceptable, even if we don't, drop the cost down. Especially since people can write new contracts that are more efficient if it's really critical.
So I had another question. I was wondering if, if you looked into how the cost would be affected if instead of charging the access cost, the chunk cost once per transaction, they were only charged once per block.
This was definitely brought up, but I think in the back when we were starting to do these like non-repeating access costs for in Berlin, and the argument in favor of making them be per transaction was basically just simplicity. Like logic to do things at the per transaction level is something that exists, whereas like these data structures that at per block level that still can get reverted is something that we don't have before, and so there's just more possibility of there being bugs if between like weird interactions between reversions and whatever. I mean that is definitely something.
It could also mean that your transaction suddenly becomes a lot more expensive if it's included early in a block and stuff like that, right?
Right. It definitely breaks independence assumptions, but then is I guess the counter argument is like, well, we have MEV and we've basically surrendered to the facts that optimizing transaction inclusion revenue is an incredibly hard problem. So, and payments for your transaction have been pretty random for a while now. Well, I guess in the sense that they're predictable, but the fee level is random regardless. And if it's a Uniswap trade, then your slippage is unpredictable and all of those things. So it's not clear that you'd be losing anything or it's not clear that the loss of invariance actually sacrifices anything that wasn't already lost.
The fairer solution to that is simply to offer a refund to the block producer that allows them to include extra transactions because there were some gas savings by repeated access?
Well, in an EIP 1559 context, like being able to include extra transactions like would mean what, like that would only apply during the congestion case, right? Like during the normal case, like would you refund them the base fee as well? And if so, then that just like that just means that they get a refund, which I think is
So I
it'd be a refund on the gas limit, not a refund on the gas fee. And it would impact 1559 because it will influence whether the base fee increases or decreases. So like our throughput would
weird.
go up.
So
like the idea here being that, like from a functional standpoint, how much it costs to execute a block is lower if every single transaction that block accesses the exact same state. But currently, we charge as though they all access different states. And so we could increase the throughput of the blockchain by amortizing that out and saying, hey, you guys all access the same state, so we're not going to raise the gas limit for the next block.
Yeah, I mean, realistic, like theoretically, you could even just refund the base fee to the like proportionally to people who access the same state. Like if 3 transactions accessed, then you refund each of them 2/3. But that's like more complicated consensus logic already.
Yeah, I think the main argument against all these is exactly what you said. It's the way the execution engines are written right now. Adding block level state that can revert on a per transaction basis would add a lot of complexity that none of the execution engines currently have the kind of architecture to deal with. And so it takes a change that would otherwise be small and makes it now a very large change just because it touches so much code. And this is just a side effect of the way things are architected right now. If this is a brand new blockchain, then I think that this would be perhaps a much better idea.
Right, yeah. Well, I mean, if this was a new blockchain, there would not like a block would just contain one transaction and the user transactions would just be calls and way to figure out how to do abstraction properly. But I still have the dream, and I think we're closer than ever.
Yeah, one other thing that I forgot to mention is that the study didn't consider other things. Like, for instance, there are some contracts which are very tied to the current Patricia Trie implementation, such as Kedonix oracles, where they use the block hash and then they accept a proof to see what the storage location was at some point in time. You know, all of those contracts will be broken, but it's, you know, they're too tied to the current implementation.
Right. I think for those cases, like we just have to accept that anything built off of current trees can't be helped. But one idea that I had for forward compatibility is that we would also, like this would be a separate EIP, but we can introduce some opcodes that do a history proof verification. And those opcodes, like when Verkle trees are introduced, they would take in Verkle proofs, and then the nice, and they would just take as input, like basically like some historical block number, a proof, and then it would just be, or historical block number key value proof, and it would just return whether or not the proof is correct. And the nice property of this is that if we later upgrade from a Verkle tree to something else, like we upgrade to like some Stark's binary tree, then the precompile could just be seamlessly updated, and like based on what the block number or the slot is, it would just automatically either expect the proof to be a Verkle proof or expect the proof to be a Stark's binary proof.
It'd be great if we can get something like that before we do the first tree migration, so that way people can have time to migrate to this new precompile off of whatever old systems they're using. That being said, there are relatively few actual people using things like the Kedonix Oracle or transaction proofs is the other one. So like the scope of, I mean, it's never fun, but like the number of people actually impacted by that, I think, is low by volume. It's just unfortunate. Like
also,
the people doing
most people nowadays still use admin keys, right? So like it would only be a problem for those contracts which aren't like upgradable for some reason.
Right. It's just unfortunate, you know, when we're the people who are hurting are the people who are doing things right. like doing proof verification and non-upgradable contracts. Like, oh, sorry, we're gonna screw you.
Yes. Well, the question is, like, I guess, like, at some point we need to be more systematic about like conveying what things like of the protocol you can rely on and what is subject to change. Yeah. And maybe we haven't done that in the past, but like, yeah.
I think just getting with enough time, people can upgrade from pretty much anything. Even non-upgradable contracts, you can still do, like Uniswap. You know, Uniswap did a V1, then V2, then V3. So if you give people enough time, they can migrate. And so I think if you just provide the tools enough in advance, like this proof verifier precompile, then people will be able to migrate whatever they've got. Like I don't think there are many contracts out there that are non-upgradable and have lasted a very long time. The only one.
Also, people who write non-upgradable contracts tend not to do like complicated, risky things like screwing around with proof of things about the Verkle tree. Like I can think about contracts we absolutely cannot change, like say the ETH2 deposit contract, but like no one's doing anything weird or complicated in that like would be broken by changing how Ethereum works.
Yeah.
One interesting thing will be, so I've definitely had some people contact me who are worried about their bridges and whatever. I don't know that, how many bridges currently do like storage proof verification and stuff like that. But yeah, they'll have to upgrade. But I think at the moment, that's not so much of a problem for Ethereum. Like everyone would just upgrade their bridge and do whatever hard fork they need to stay compatible with the Ethereum chain. But it might become a problem for other chains when Ethereum, say, probably won't hard fork to stay compatible with another chain's upgrade.
So that seems to be all the questions or comments. Anything else anyone wants to add before we wrap up?
Keep up the good work, everybody.
Yeah, thanks a lot for joining. Yeah, and we will continue conversations on this in the execution dev channel on Discord.
Sounds good.
Okay, have a good one.
Thank you.
Thank you.
Or whatever time it is.
Bye.